Awesome. Okay. So I work for Nearform. We build a lot of microservices. The very first microservice system that we built was in 2011. Of course, we didn't have the buzzword back then. We didn't know what we were doing. But it seemed like a good idea to hook up a whole bunch of Node.js processes using Redis and use a messaging flow between them. And we kind of got hooked on this architecture. And then we invited Fred George to speak at our meetup. And he gave us the name, and he kind of legitimized what we were doing. And that got us really fired up. The interesting thing about our work is, because we're a consultancy, we get to see a lot of different architectures. We get to see a lot of different takes on this approach, which is really, really awesome, because we can see all of the different challenges, but we can also assess all of the ways that people are trying to solve these problems. And part of the reason that we organized this one-day conference is to help share all that learning, to bring everybody here together to learn how to do microservices better, because we're still at the start of a journey. We're still trying to understand the best approaches and the best way to do things. And we have to learn from each other. So this is the flight deck of the Space Shuttle Atlantis. This is a picture taken from mission STS-101. The software that runs this vehicle is some of the most perfect software ever written. The release cycle, they have one bug every 3 months on average. Each line of code costs about $1,000. So this is awesome engineering. This is something to look up to. The problem is that when we build software in other contexts, we implicitly try to build software like this. We have an implicit expectation of ourselves. It's not even the business. Ourselves as developers, that we're trying to build perfect software that has no bugs. And when you try to build software like this, you end up being incredibly slow, because it's very hard to make iterative changes. You have to take a different approach. And if you take a look at a different way to solve the problem, you go from saying, how do we measure what we're doing in terms of the code, to how do we measure what we're doing in terms of the business outcomes. Fred mentioned that in his talk at the start, and it's very instructive to take that view. This is another aircraft. This is the Gossamer Albatross. This is the first human-powered aircraft to fly across the English Channel. And it did so in 1979. This aircraft was built to win an engineering challenge, an engineering prize. The prize was £100,000 for the first human-powered airplane to fly across the Channel. And it was first offered in 1959. Many people attempted to build aircraft that could do this. This is basically like a flying bicycle. The problem was that these engineering teams would spend a year thinking really hard about the problem, coming up with a wonderful design, building the aircraft, and then they would get in, and a couple of hundred yards, the pilot would be completely exhausted and the plane would crash. The engineer that eventually figured out how to do it was a guy called Paul McCready, and he realized that the real problem wasn't flying across the English Channel. The real problem was building an aircraft that could do that. And to do that, you needed to be able to iterate quickly. So instead of thinking about designing an aircraft, he thought about a process for designing the process for building an aircraft. And he came up with a set of components using aluminium and wiring and mylar that let him iterate on the design. And within a year, he had solved the problem, because he could iterate quickly. He was building 3-4 airplanes a day. And often they would crash. But he accepted the fact that the system that he was building was not perfect. It was more important to move fast. So this is a yak. It's It's a symbol of enterprise software development. This yak is in the Himalayas. Put your hands up if you know where I'm going with this. So you're in an enterprise software development team, and it turns out that you need a new version of component. Your retail e-commerce website needs to support multiple currencies. So somebody writes a component that handles multiple currencies. Turns out they have a dependency on some jar. Turns out that jar only works with the latest version of Java. Now you need to install the latest version of Java. Turns out that doesn't work with your current operating system, so now you have to upgrade your operating system. That doesn't work on your current laptop, so now you need to buy a new one. This keeps going. Eventually, you end up having to climb the Himalayas and shave this yak. Why? Because monolithic development has so many interconnections, so many interdependencies. You can't change one piece. You can't pull a thread without everything falling apart. It's really instructive, the charts that Adrian just showed you, the donut diagrams, where he could categorize the components in his system. It would be impossible to do that with the objects or the components or the modules in a monolith, even if you could call them that, because they're so interdependent. The really nice thing about the microservices architecture is that it gives you this homogeneous unit. It's a unit of deployment. It's a unit of measurement. It's a unit of development. It's a unit of functionality. It gives you a really nice way to contain the complexity, which brings you back to what you really want to do with software. This picture is from, it's an ad for Lego from 1981. And it's really cool, right? That's obviously a future engineer. The really interesting thing about Lego, and people often use Lego as an example of a component model, but the interesting thing about it is I can add a brick without having to change any of the other bricks. And the bricks are relatively homogeneous. They fit together easily. It's a component model. And despite all of the other interesting features of the microservice architecture, the most important piece in our experience is the fact that it is a component model for software development. A model that lets you take units of software and compose them together. Fred talked about a system that calculated insurance quotes. And the interesting thing about the system that he described was to enhance its functionality, you added new microservices. You didn't change existing ones. You added new ones. A good component model gives you this characteristic, additivity. It's easy to add stuff because you don't have to change other things. So what are microservices anyway? For us, they've always got to be small processes that are independent from each other, independently deployable. They communicate via messages. So please learn from Adrian's example. Do not write SDKs or jars or client-side libraries that expose your microservice. Don't do that. It has to be a uniform messaging API. And then there's this powerful component model, which, again, for us is the most important piece. And why use them? Why go to all this trouble? For us, it's about avoiding technical debt. The number one drawback of the monolith is that it builds up technical debt. You end up yak shaving. Microservices let you avoid that problem. And they also make continuous delivery much easier. Think about what deployment means in a microservice context. The unit of deployment is a microservice. When you deploy, you're deploying one instance of one microservice. And if that breaks stuff, rolling back is you just turn the microservice off, turn the Docker container off. You can deploy individual instances, and you can measure the effect on the system. It's really powerful, and it really reduces the risk of deployment. You don't get these big bangs. And all of this stuff lets you move really, really quickly, because you can add features without having knock-on effects in the rest of the system. Well, there are trade-offs, for sure, right? There's no such thing as a free lunch. Deployment is definitely more complex. You have to automate. You can't just do things the old way. Essential to automate deployment. It is a weird programming model. And that's because you have to think in terms of messages. You don't get to think in terms of traditional linear flows. And then another problem which has arisen in practice, which we found to be kind of a core issue. Services have to find each other. So if I have microservice A and microservice B, and microservice A needs to send a message to B, how does that happen? Is this a diagram of microservices, or is this a diagram of objects, and one object calling a method on another object? If your microservices know about each other, if A knows about the identity of B, that's actually a really nasty coupling. It's not something that you want. This issue of identity is a key problem, because if I send a message and I know who the message is for, that's knowledge that A has of B. That's coupling. Really, you want the world to look like this. A sends a message, and it doesn't know who's going to get the message. And B receives messages, and it doesn't know who it received the messages from. Now you're fully decoupled. You can deploy different versions of A and different versions of B. If you think about the Kafka architecture that Fred talked about earlier, you can see that it's a way of enabling this, because messages go onto the queue, and you wait for responses for 300 milliseconds, and they come back, and you don't know who produced the responses. This is what enables you to do deployment of multiple versions of microservices. This is what allows you to migrate your schemas, your message schemas. But we still have a practical problem. A still needs to find B somehow. And if we look at the solutions that people are using in practice, we have to ask the question of each solution, does it still create this issue of identity? Are we still exposing the identity of B? So you could bake configuration files into your Docker containers. You can use intelligent load balancing. So Netflix Eureka is a good example of that, or you could bake your own. You can have service registries. So register the location of your services in console. Use DNS. DNS is nice and scalable. Or you could use a message bus. The problem with each of these methods is that they expose identity to some extent. The host and IP address of the service, perhaps. The message queue topic, that's a weak form of identity. For the load balancer, the URL endpoint, again, these are all things that identify B in some way. It doesn't give us this. It doesn't give us this idea of throwing messages out into the universe and not knowing where they end up. Again, the reason that we want to do this is we want to have a component model, because if you can swap components in and out, you can move faster. And if a component depends on another component, you can't do that. This is a page from a book called 507 Mechanical Movements, which was published in 1868. And if you look up 507 mechanical movements on Google, somebody took this book and produced animated versions of all these things. It's really, really cool. The point is, we're building software machines. We need to have these reusable components. And somehow, we've got to find a way to decouple them. So this is where our experience building microservices systems kicks in, because we tried all these techniques, DNS and message buses and service registries and all this stuff, all this type of thing. And they've caused different types of problems. But we've distilled two really useful concepts or principles out of our approach, which help us move towards this decoupled world. And these principles are pattern matching and transport independence. Pattern matching is what lets you decouple identity. Instead of knowing about B, you send out messages, and B simply deals with the messages that it cares about. It pattern matches the universe of messages and deals with ones that it cares about. And I completely elide the question of how does it do that. The implementation is not important. There are ways and means of doing this. What's important is the concept. As a developer building a microservice, I only pay attention to messages that I care about. Transport independence is saying it's not important how messages get from A to B. When A sends a message, maybe it goes over a bus. Maybe it's HTTP. Maybe it goes to Redis. It shouldn't matter. It also doesn't matter if the message ends up in multiple services or not. What does this mean in practice? Now, here's an example. Let's say microservice A is sending a message, and the message is the King of Hearts. How does that get to B? With pattern matching, B says, I am interested in all heart cards. I don't care which card it is, but if it's a heart suit, I want that message. These things are still decoupled. These are not message types. I'm not saying that B responds to the message type King of Hearts. I'm saying B responds to the heart pattern. This is what gives you the decoupling. So you have this idea of blind messages. Services don't know about each other. They are they exist completely by themselves in their own universe. They send messages into the world, and they receive messages. They only receive the messages they care about. Of course, you need an infrastructure to provide this. It is a useful fiction that your infrastructure provides. But from the perspective of the developer, this is a very useful world to be in because it lets you move fast. It lets you get lots of the benefits of microservices. So how do we actually implement this? Because it can be done in various ways, and you can use all of the techniques that I've discussed, like message buses, to kind of do it. But we've, in the last 6 months, started experimenting with a peer-to-peer approach. This approach is sort of a radical inversion of a traditional approach to designing an architecture, because the infrastructure piece actually has every single service knowing about every single other service. So if I have 1,000 microservices, every microservice maintains a table of 1,000 entries. This is hidden from the developer. It's hidden from the business logic. But each individual microservice knows how to send a message to the specific set of microservices that match the pattern for that message. How do you get this to work? Well, recently a very nice algorithm has been released, and it's called the Scalable Weakly Consistent Infection Style Process Group Membership Protocol. And it's awesome. It's as awesome as it sounds. Instead of broadcasting the messages to everybody, which is inefficient and will never work, you randomly broadcast to a small subset. And this algorithm is very, very efficient at spreading global knowledge without saturating the network. And briefly, the way it works is every service, once a second, randomly pings a small subset of other services, checking to see, do they respond? Are they up? Now, the interesting thing about this is I don't need to wait 30 seconds to discover if a service is down because I have a large sample size. 30 services will detect if an individual service is down. And then I can spread that knowledge on my next ping. So my pings also carry information that piggybacks. So when I ping a service, if that service is alive, I also send information that says, hey, this other service is dead. Or if a new service joins, it announces itself to just one other service and says, hey, I'm here. So in this case, the pink service is joining the network. It announces itself to the orange service. And the next time the orange service pings a small random selection, it says, hey, there's this new pink service. And then when all of the services that it has pinged ping, that information disseminates further. You get convergence, which is complete knowledge of the entire system, typically within a few hundred milliseconds. Uber has taken this up to 2,500 services. So it's an extremely robust algorithm. Our use of it has given us a lot of confidence. We haven't come across funnies. It tends to work really, really nicely. From a software architecture perspective, it does mean that every service has to include a small client library. Now, this is not the same type of anti-pattern as Adrian was talking about. The library is the same for everybody. And it's simply a implementation of the swim algorithm and maintains the global knowledge of the network. And it's a piece that does the pattern matching. when a service joins the network, it announces the patterns that it cares about, and that knowledge goes all over the network. And this lets you do a couple of really interesting things. So what architecture patterns can you implement with this approach? Well, here's one. I can scale really easily. I can scale easily because when I add new instances of B that match the heart pattern, that goes into the global table that A is maintaining. So scaling is simple. I don't need to have load balancers. I get scaling for free. This is potentially an actor model where you round robin between all the instances of B, but I don't have to do that. I could also have a publish-subscribe model. So instead of round robining, I can send out the message to everybody who's interested in it. I don't need to use a message bus. I don't need to use a load balancer. I don't need to use any other pieces of the network. I don't need to use agents on my virtual machines to do any of this stuff. Each service has global knowledge. This can be implemented as a for loop. I just loop through everybody I know about that cares about hearts and send them a message. It also lets me implement that really important principle that Fred talked about, which is going from the general to the specific as you develop the system. So the way that we build systems and the way that lets us move fast is you build general solutions first and then you refine them. Let's say I'm building an HR system. In the first iteration, I build a generic user profile service. And then I have to deal with users that are employees or contractors or trainers, let's say. The contractor profile might be slightly different. Instead of modifying my data structures and my database schemas and my user profile service, I write a new microservice that deals specifically with that case. So in this diagram, the B microservice deals with the generic heart messages. But I have a special case, C, that deals with the ace of hearts. And any ace of hearts messages go to C instead of B. And as I refine my system iteration by iteration, as I add new features, I capture smaller and smaller subsets of messages. I'd never change the code of A and B. This is where you avoid technical debt. You don't have to go back and refactor any of those other microservices. You don't have to refactor your data structures. You're just using pattern matching on the message itself. Another interesting thing that you can do is you get composability. So this is where the component model really kicks in. If you read some of the original papers that Alan Kay wrote about Scheme and how what the original ideas behind things like Scheme were, or if you look at some of the talks by Gerald Sussman, the whole idea is to have systems where you can take components and you can compose them together. Composability is hard to achieve. A good example would be Unix pipes, for example. So you can compose together small command line utilities because you have a homogeneous API between them. Messages give you a homogeneous API as well. And you can compose microservices using messages. In this example, I've placed the C microservice in front of the B microservice. So C might be a caching microservice, for example. And to get to this state, I start with my original B matching heart. I then add C, which matches heart as well, but it emits heart prime. And then I add B, a new version of B, or perhaps I just change my configuration for B to say B now also matches heart prime. Once this is up and running, I then turn off the old versions of B that don't know about heart prime. And I have a seamless, zero downtime transition from a system with no caching to a system with caching. Again, the code inside B didn't change. I didn't need to start adding if statements or changing my ORM layer or any of that sort of stuff to add caching. And it doesn't have to be caching. It could be message validation, auditing, whatever. I've added a cross-cutting concern to my system without changing any code. OK, so this is all theory. There is an example where you can see this in practice. So this is Node.js. This is a Node.js code base. It's a small Twitter clone in 14 microservices. But it's not a toy system. It's actually a system that will scale to millions of users. It implements that caching for tweet storage. It implements sharding for storage. It implements fan-out. So the way that Twitter scales is that you have a fan-out service that injects tweets into everybody's timeline. It provides that. It shows you how you can deliver different pages using different microservices. Obviously, you need a library that's going to do the swim algorithm. You need something that's going to give you the pattern matching. For Node.js, this is the one that we've been working on for the last 5 years, since 2011, senecajs.org. It gives you that infrastructural component that makes all this possible. And finally, I'm kind of trying to put all these ideas down on paper. So I'm writing this book called The Tao of Microservices, which is sort of a higher level description of all of these architectural approaches. And it's on early access. The first 3 chapters are out. And it is not about implementing microservices in Node or Scala or anything like that. It's about taking this pattern matching and transport independence approach, taking the idea that you can have failures in the system, that the way to move fast is to not try to rebuild the Space Shuttle Atlantis, focus on the business outcomes, and microservices enable you to do that. Thank you very much.
Thanks very much, Richard. I think if I was